Good afternoon, everyone. I welcome you all to the problem solving session for the NPTEL course Fluidization Engineering. So, the course instructor is Professor Subrata K Majumder from the Department of Chemical Engineering, IIT Guwahati, and the live sessions are handled by myself, Anchor Karthika, from IIT Hyderabad. So, I am a research scholar. So, moving on, we are now into week 12 of the course. So, by now, we all know what the course Fluidization Engineering is all about, since we have covered almost everything in the basics related to fluidization engineering. So, the looking at the course layout, now we are very well aware of what we have seen, and we have almost covered the basics and the problems from the basic concepts. So the first few weeks it was about the introduction to the phenomenon of fluidization, advantages and disadvantages of fluidized beds, and the various industrial applications. So, since we all know what fluidization engineering is, can anyone just recollect and mention what fluidization is? So, basically, fluidization is nothing but the process in which we pass fluid inside the packed bed. The fluid is passed at a sufficiently high velocity such that the particle starts to move and their behavior resembles that of a fluid. So since now the particles have started moving, the contact area of the particles is enhanced. Thereby the fluid solid mass transfer or the heat transfer phenomenon is also enhanced, and so it becomes useful in various applications like catalysis, regeneration, and coating, drying of solids, so many things. So what are all the disadvantages? We have certain disadvantages like uh, the erosion of the particles, as the particles might escape, so that we cannot use higher costly materials in these applications. So later on, we have also seen how fluidized beds, solids, are classified into four classes by GELDAT, depending on their size and the relative density between the fluid and the particles. And based on the classes under which those particles fall, the particle behavior would be different. For example, the smallest of the particles comes under the class gel.c, and it is very difficult to fluidize such particles because in these particles the cohesive forces play an important role, thereby the particles get stuck to each other rather than moving freely. So it is difficult to fluidize such particles. On the other hand, gel.A particles are comparatively larger in size, and it is less difficult to fluidize, and uniform fluidization occurs in these beds. The FCC catalyst comes under the gel.A class, and the further larger particles comes under gel.B particles, and the difficulty associated with these is these beds actually form bubbles, and when we use gas as the fluid, and because of that reason, we need to have a clear understanding of the phenomenon of bubbling inside the bed for us to have a proper control of the operation. And the largest size particles comes under gel.D particles, in which the bed or the bubbles become very much vigorous, and we use the spouted beds. So also, apart from this, there are various regimes of fluidization based on the inlet fluid velocity. So when the fluid velocity is very low, the particle does not move. So we call it as fixed bed or packed bed. And with increase in velocity, the pressure drop also increases inside the bed. So at one point there comes a constant pressure drop inside the bed. Like after that point, how much ever we increase the velocity, the pressure drop remains a constant, and that particular point is known as minimum fluidization or incipient fluidization. At that point, the particles do not move but they remain in the loosely packed state. So, after minimum fluidization, with increase in the velocity, we are able to observe the constant pressure drop and the particles also start to move inside the bed. So, there comes up various regimes. The first one is that if we use liquid as a fluid, we can see the smooth fluidization happening. There would not be any bubble formation. On the other hand, if we go with gas as a fluid, we are able to see bubbling fluidized beds, and these bubbles start increasing in size with increase in the velocity of the fluid. So there the bubbles start increasing in size and they almost become size of the bed, and later on the bubbles start bursting and there becomes a turbulent motion. So we can see various regimes like bubbling fluidized beds, slugging fluidized beds, turbulent beds, and fast fluidized regimes, fast fluidization. So after that, we can also see pneumatic transport where the particles escape from the bed, and there comes a need for recirculation of the solids so that there is no material loss and also the optimum level of solids inside the bed is being maintained. So there also comes various equations in the literature to study the pressure drop and happening inside the bed. So also, like we have seen very recently the solids movement inside the bed and also the mixing, segregation, and the staging. So when we pass the fluid inside the bed, uh, like if there is a single particle, we are just studying the hydrodynamics, but if there are in industries, we'll be using a multiple size particles or multiple particle density range of particles. So there happens mixing phenomena or segregation phenomena, we do not know. So those things also we have studied, like how mixing is happening depending on our requirement. Sometimes mixing would be favorable and sometimes segregation would be favorable. So we can optimize the bed performance based on certain factors and get our desired results. So later on we have seen the gas distributor type. There are different types like porous plate distributor, perforated plate distributor, tear type distributor, and bubble cap type distributors. So the same distributor type that we use in lab scale cannot be used in the industry scale. Why? Because the pressure drop becomes an important factor at the such large scales, and we cannot use the ones which we use in the laboratory scale, because if there is a large pressure drop, it leads to increased pumping capacity and therefore higher power consumption. So all these are controlling factors. And then the most important thing is we have been saying bubbles grow inside the bed and bubbling occurs. So also we have seen that why it is important to know the bubbling characteristics inside the bed. Therefore, bubbling fluidized beds and the phase gas dispersion and the gas interchange in the bubbling beds and mixing characteristics have been studied, and also entrainment and elutration from the fluidized beds, which is nothing but the escape of the solid particles from the bed, and how we will be we can also selective removal of solids might also happen from the fluidized beds. So those things we have seen. And then it is about attrition mechanisms. Attrition is just that which we have breakage of the particles, and by shear forces or fractional breaking, like surface wear and tear can also be there, or fragmentation of particles can also be there. So for that also we have seen different models. And the last, it is about mass transfer phenomena happening inside the bed, particle to gas mass transfer and its analysis in two phase and three phase systems and modeling, and also about the heat transfer phenomena, heat transfer between fluidized beds and surfaces and modeling. So now it is about books and references. So the first one is Cooney and Levenspil's Fluidization Engineering, by Butterworth 1991. And second one is Gillespie's multiphase flow and fluidization continuum and kinetic theory description. And third one, Gibbler fluidization dynamics. And fourth one is K Majumder's hydrodynamics and transport processes of inverse bubbly flows. So we have seen in detailed about what each books represent and which one to follow. So we'll now start with the today's session. So before going on, I'll give you an overview. So in today's class, mostly we'll be seeing with the mass transfer and the heat transfer phenomena happening inside the bed. So the first few problems will come from come similar to the week 12 problems, and the next few problems come similar to the week 11 problems. That is week 11 assignments. For those solutions have been released, we are seeing the problems, and week 12 also we have seen. Week 12 problems are similar problems, while week 11 problems are exact assignment problems. So now we'll see. So the first question is about the resistance of mass transfer in the liquid phase at the liquid solid interface is equal to dash, where K is the mass transfer coefficient, Kr is the rate constant, and A is the surface area of solid per volume of bed. So here you must be very aware that the question asks about the resistance of mass transfer in the liquid phase at the liquid solid interface. So you would be very well aware that each interface has different equation. So you must be careful of what the question is demanding. So in this particular question, the question is about the resistance of mass transfer in the liquid phase at the liquid solid interface. So the options we look at: option A, it is 1 by kgA, and option B, 1 by m KL A into EA, and option C, 1 by m KS AP, and okay, it is B. A by m KR AP. So the right answer is actually, since we are dealing with the liquid solid interface, it is option C, 1 by m KS AP. So it is liquid solid interface and the resistance of mass transfer in the liquid phase. So for this is for gas, and this is for gas liquid interface. This is gas solid gas liquid interface, this is liquid solid interface, and this is when reaction happens inside the system. So option A is for gas solid, and it is gas liquid interface, and it is liquid solid interface, and this is when reaction happens inside the system. So therefore, since our question is about resistance of mass transfer in the liquid phase at the liquid solid interface, it is option C. Option C is the right answer. Now we will move on to question 2. In question 2, one may assume that the solids do not affect the value of KLA when option A, solid concentration is very high, option B, solid concentration is very low, option C, solid concentration is moderate, none of the above. So actual answer is option B, solid concentration is low. So what the question is about? It is about one may assume that the solids do not affect the value of KLA when dash. So when solid concentration is low, the solids do not affect the value of KLA. If the solid concentration is high, it certainly affects. So here it does not affect the value of KLA when the solid concentration is low is the right answer. We will move on to question 3. Consider UG is less than 8 cm per second and mu effective varies within the range of 1 to 100 MPa second, and millipascal second, and after fitting data in mu f is equal to k into gamma effective n minus 1, the slope and intercept were found to be minus 0.8 and 4. Thus, What will be the flow behavior index and flow consistency index? Where Ug is the velocity of gas and mu effective is the effective suspension viscosity and gamma effective is the effective applied shear rate. So the question is a very simple problem where you are just required to fit the graph. I mean, you are not even required to fit, already the fitting is done and the slope and the intercept is given, and based on that you are asked to find the flow behavior index and flow consistency index, which you can effectively obtain from the equation given. So I'll give you the options and I'll give you 1 minute time as well. So in the meantime, you should just substitute the values and get back with the answer. So options are option A, n is equal to zero point 0.2, k is equal to zero point 0.4. Option B, n is equal to 0.15, k is equal to 1000. Option C, n is equal to minus 0.8, k is equal to 400. Option D, n is equal to zero point 0.2, k is equal to 10,000. So I'll give you guys a minute time. So coming back, answer is actually n is equal to zero point 0.2, k is equal to 10,000. So we'll see now how to get the answer. I hope most of you would have got the answer by now, but still for rest of them we will solve. So first one, we'll write the given. Given it is Ug is less than 8 centimeter per second and mu effective varies within the range of 1 to 100 millipascal second. And we are given that after fitting data in this particular equation form, the slope is minus 0.8 and intercept is 4. So now we are asked to find the flow behavior index n and fluid consistency index k. So k is there and n is also there. So since the fitting is in this particular equation, we'll just expand this. So let it be. So the solution is such that mu effective is equal to k into gamma effective n minus 1. So we are just taking the log on both the sides since we need to have an intercept as well as the slope. So if we take these things, we can just plot it in the log graph and get the things. So it is log of mu effective is equal to log of k into gamma effective n minus 1. And again now we are splitting this one. Log of mu effective is equal to log of k plus log of k gamma effective into n minus 1. I mean to the power of n minus 1. So since log a to the power of b is equal to b into log a, we are just taking the n minus 1 as the product term and rewriting it as n minus 1 into log of gamma effective. And now we know that log of mu effective is there, log of k is there, log plus n minus 1 log of gamma effective. So here it is of the format y is equal to m into x plus c. So since c is the intercept and m is the slope, we have the value of slope as well as the intercept. So intercept is given as 4. So log k is equal to 4 and k is equal to 10,000. Similarly, slope is minus 0.8, n minus 1 is equal to minus 0.8, therefore n is equal to 0.2. So I hope it is clear. So now we'll just go through the things again one more time. So first it is given that Ug is less than 8 centimeter per second and mu effectiveness varies within the range of 1 to 100 millipascal second. And after putting the data in the given form, mu effectiveness is equal to k into gamma effectiveness n minus 1. We are given the values of slope as well as the intercept. Slope is minus 0.8 and intercept is 4. And now we are supposed to find the flow behavior index and flow consistency index. So both the factors are given in the equation itself. So just we need to rearrange the equation and get the intercept and the slope. So for us to get the equation in the form with slope and intercept, the equation should be of the form y is equal to mx plus c, where m is the slope and c is the intercept. So now we are rewriting the equation by taking log on both sides. So mu effectiveness is equal to k into gamma effectiveness to the power of n minus 1, and we are taking log on both sides. So log mu effectiveness is equal to log of k into gamma effectiveness n minus 1, and the LHS remains the same, and this one we are just rewriting. So log of a into b is equal to log a plus log b. So it is log k plus log of gamma effectiveness to the power of n minus 1, and again log a to the power of b is equal to b into log a. So this one n minus 1, again we are taking to the front n minus 1 into log of gamma effectiveness. So in this particular form of equation comes under y is equal to mx plus c. So c is the intercept, so log k is equal to 4, and we are taking anti-log and we are getting the value of k as 10 to the power 10 to the power of 4, which is 10,000. Similarly, log n minus 1 is equal to minus 0.8, and since this n minus 1 is equal to minus 0.8, n is equal to 1 minus 0.8, which is 0.2. So n is equal to 0.2, k is equal to 10,000. So now I think it is the same. I mean, we are getting the answer. So n is equal to 0.2, k is equal to 10,000. So it should be clear now. We will go to next problem. Next question. What will be the volumetric mass transfer coefficient if AB is the interfacial area per unit volume of bed and K is the mass transfer coefficient, dB is the effective bubble diameter, gamma is the bubble fraction in a fluidized bed. So this particular question actually comes from week 10 or week 11, I guess. So it is about mass transfer, right? So options are KAB is equal to K into 6 gamma by dB, and option B KAB is equal to K into 3 gamma by dB, and KAB is equal to K into gamma by dB, and option D KAB is equal to K into 6 gamma by dB square. So answer is actually option A. KAB is equal to KAB is equal to K into 6 gamma by dB. That is the answer. So volumetric mass transfer coefficient is this. So if AB is interfacial area per unit volume of the bed, K into AB is equal to K into 6 into delta by dB, where delta is the bubble fraction in a fluidized bed and dB is the effective bubble diameter. So moving on to the next question, we have gas hold up increases when bubble diameter dash. Option A increases. Option B decreases. Option C remains constant. Option D unpredictable. So this question is about what happens when gas holdup increases. So we have bubble diameter, and if the bubble diameter decreases, then gas holdup increases. So answer is option B. Moving on, we have question 6 over here. The enhanced gas absorption for heterogeneous system can be analyzed by the model of dash. Option A, Winke 1992. Option B, Kars et al. 1979. Option C, Holstwood et al. 1988. Option D, Pandit and Joshi 1986. So since the question is about enhanced gas absorption for heterogeneous system, enhanced gas absorption for heterogeneous system based on film theory, it is based on the model of Winke et al. 1992. So option A is the right answer. So the gas to liquid mass transfer rate of component A can be enhanced by the presence of particles due to option A, adsorption of the particles. Option B, catalysis by the particles. Option C, reaction with the particles. Option D, all of the above. So this question is a very simple question, and it just asks the gas to liquid mass transfer rate of component A. It would be enhanced by the presence of particles. So there is a gas to liquid mass transfer rate for the component A, and if particles are present, it just enhances that. And which is the main reason for that? Is it adsorption on the particles, or it is catalysis by the particles, or is it reaction with the particles? So the answer is actually all of the above is the right answer. Option D is the right answer. Moving on, for question 8 we have the rate of heat transfer between particles and gas per unit bed volume is exceptionally high because of the dash interfacial surface area. So this is what we have been saying every time, that is as the bed is fluidized, the rate of heat transfer is enhanced. Why? Because the interfacial surface area is increased. So the answer is actually increased. So we look at the options once. So option A, it is small. Option B, it is large. Option C, it is unchanged. Option D, it is tiny. So as we know, it is increased, or in other words, it is large. So option B is the right answer. So here the rate of heat transfer between the particles and the gas per unit bed volume is exceptionally high. We are given it is exceptionally high, and it is because of the increased surface area, increased interfacial surface area. Increased interfacial surface area. The rate of heat transfer between the particles and gas per unit volume is exceptionally high because of the large interfacial surface area. So that is the thing. And moving on to question 9, we have heat transfer coefficient not increases with dash. Heat transfer coefficient not increases with dash. Option A, increasing thermal conductivity. Option B, increasing density. Option C, increasing viscosity of the gas. Option D, increasing velocity of the gas relative to the particle. So looking at the options, the first one is increasing thermal conductivity. If thermal conductivity is increased, the heat transfer coefficient actually increases. And similarly, increasing the density also increases the heat transfer coefficient. But increasing the viscosity of the gas, heat transfer coefficient is not increased. On the other hand, with decreasing viscosity of the gas, you are able to increase the heat transfer coefficient, but the reverse is false. heat transfer coefficient not increases with increasing viscosity of the gas. So heat transfer coefficient increases with decreasing, I think I am confusing you. Heat transfer coefficient increases with decreasing viscosity of the gas, and similarly not increases with increasing viscosity of the gas. So heat transfer coefficient increases with increasing thermal conductivity, and heat transfer coefficient increases with increasing density, and it not increases with increasing viscosity of the gas, and it increases with increasing velocity of the gas related to the particles. So to have a more clear understanding over here, we look at it clearly. So what is given? Heat transfer coefficient not increases with. So we'll see where it increases. So it increases with increasing thermal conductivity, it increases with increasing density, it increases with decreasing viscosity of the gas, it increases with increasing velocity of the gas related to the particles. So here it not increases with, so the right answer is option C is the right answer. Increasing viscosity of the gas is the right answer. I hope it is clear and I didn't make you guys more confused. So question 10, it is about the gas liquid heat transfer in three-phase fluidized bed can be determined with assumptions. Option A, intraparticle temperature gradient is neglected. Option B, liquid side resistance to heat transfer is neglected. Option C, well mixing in the three-phase system is achieved by the presence of solids. Option D, all of the above. So answer is actually option D, all of the above. So why? The gas liquid heat transfer in three-phase fluidized bed can be determined with assumptions. So here it is about gas liquid heat transfer, and that too in a three-phase fluidized bed, and it is determined with assumptions. Intraparticle temperature gradient is neglected. So yeah, this is true. Since we are now dealing with gas liquid heat transfer, so we are neglecting the intraparticle heat transfer temperature gradient. And liquid side resistance to heat transfer is neglected. Again, this is true. And well mixing is achieved by the presence of solid phase. Again, this is true. I mean, these are all the assumptions with which it is determined. So moving on, we have question 11. So like in case of clouded bubbles at plug flow, which of the following condition is correct for apparent heat transfer coefficient H bed between gas and bed based upon the total surface area of particles and real heat transfer coefficient between gas and the single particles? Options are, like before moving we'll see. So here we have clouded bubbles at plug flow, and which of the following condition is correct? We have to identify which of the following conditions are correct. So the first one is apparent heat transfer coefficient between gas and bed based upon the total surface area of particles. So here we have apparent heat transfer coefficient and real heat transfer coefficient. So the apparent heat transfer coefficient is given by H bed, and it is between gas and the bed based upon the total surface area. And the next one, it is real heat transfer coefficient. It is based upon the gas and the single particles. So, and also the condition given here is it is a clouded bubbles at plug flow. So we'll look at the options, and option A, it is H bed is not equal to HP, and option B, H bed is less than HP. Option C, H bed is equal to HP, and option D, H bed is greater than HP. So answer is actually option B. H bed is less than HP. Why? Because the apparent heat transfer coefficient is between the gas and the bed, and it is based upon the total surface area of the particles. And since it is a clouded bubbles at the plug flow, it would be less than the real one between the bubble, I mean between the gas and the single particle. So a gas and a single particle will have a large heat transfer coefficient than the case of the system where it is between the gas and the bed based upon the total surface area of the particles, because here it is clouded bubbles at plug flow. So this is the condition over which it would be true. H apparent, that is apparent heat transfer coefficient, H bed is less than Hp, because in the apparent heat transfer coefficient it is considering the total surface area of the particles, and because of the presence of clouded bubbles and so on other components, this would be comparatively low between the real heat transfer coefficient between the gas and the single particle. So gas and single particle would have a higher heat transfer coefficient. So logically also that would make sense, right? Now moving on to question 12, we have wall heat transfer coefficient is smaller than heat transfer coefficient for single phase gas convection. Wall heat transfer coefficient is smaller than heat transfer coefficient for single phase gas convection. Option A true, option B false. Okay, wall heat transfer coefficient in actuality is very much larger than heat transfer coefficient for single phase gas convection. So for a single phase gas convection, wall heat transfer coefficient is very much larger than the heat transfer coefficient for single phase gas convection. So it is given opposite, so this is false. Question 13. We have, which of the following approaches are valid for modeling convective heat transfer processes? Option A. Heat transfer surfaces contacted alternatively by gas bubbles and packets of closely packed particles. Option B. Combining gas and particle convection. Option C. Correlating particle motion in fluidized beds and kinetic motion of molecules in gases. Option D. All of the above. If it is a convective, it should be all of the above. Yeah. It is all of the above is the right answer. Why? Because which of the following approaches are valid for modeling convective heat transfer processes? The first one is heat transfer surface is contacted alternatively by gas bubbles and packets of closely packed particles. So whatever the surface we are considering, it is alternatively contacted by the gas bubbles and also by the packet of solid particles, and also combining the gas and the particle convection, and then correlating particle motion in fluidized beds and kinetic motion of molecules in gases. So it is all of the above because it is convective heat transfer process. So we are considering the gas bubbles and particles, gas and the particles, and the correlating particle motion in fluidized beds and the kinetic theory of molecules in gases, like gas particle, particle, and bubble particle. So all of the above is the right answer. So now we will go to question 14. In question 14 we have, what should be the pitch to diameter ratio for tubes in the bundle for better mixing in the fluidized beds? So we have some internals placed in the fluidized beds for certain applications. So if that is the case, what should be the pitch to the diameter ratio for the tubes in the bundle in order to achieve better mixing inside the fluidized bed? So answer is actually I think 2 to 4. But we'll look at the options once. Option A 2 to 4. Option B zero point 0.1 to zero point 0.5. Option C zero point 0.5 to 1. Option D 1 to 1.8. So my guess, I would place my answer on option A, that is 2 to 4. So 2 to 4 is the pitch to the diameter ratio for tubes in the bundle for having better mixing inside the fluidized beds. So answer is option A is the right answer. Now we'll go to question 15. In question 15 we have that wall heat transfer coefficient decreases with a dash. Wall heat transfer coefficient decreases with dash, and here water heat transfer coefficient is given by the symbol HW. So H is the heat transfer coefficient and W denotes wall. So first one, option A, it is increasing solid mass flux. Option B, increasing gas velocity. Option C, increasing particle diameter. Option D, increasing radial position towards the bed wall. So look at the options and let me know the answer. So since it is just a simple one, so answer is actually option C. Increasing particle diameter is the right answer, because when solid mass flux is increased, heat transfer coefficient is increased, and increasing gas velocity, again wall heat transfer coefficient increases, but it decreases with increasing particle diameter, or on the other hand increases with decreasing particle diameter, because the heat transfer surface would be enhanced with particle diameter decreasing. So here it decreases with increasing particle diameter, and again increasing radial position towards the bed wall. So answer is option C. And moving on, we have question 16. The circulating fluidized bed has significant role in FCC, fine particles, driven solids from the bed, all of the above. So answer is actually all of the above is the right answer. So all of the above is the right answer. Circulating fluidized bed has a significant role in FCC fluid circulating catalyst, I think, and has fine particles, has driven solids from the bed. So the right answer is actually option D. All of the above is the right answer. Question 17, it is about, consider all the particles are uniformly dispersed in the gas. Thus, if gas particles in plug flow up the reactor, the constant efficiency will be dash. Consider all the particles are uniformly dispersed in the gas. If gas passes in plug flow up the reactor, the constant efficiency will be dash. So option A unity, option B 0, option C infinite, option D none of the above. So answer is actually option A unity, because here all the particles are uniformly dispersed in the gas. So if gas passes in a plug flow up the reactor, the constant efficiency will be unity. Option A is the right answer. Question 18 we have, consider all the particles in a circulating fluidized bed are evenly dispersed in the gas. Furthermore, if the gaseous phase passes in the tubular flow pattern in the reactor under a pneumatic conveying condition, the contact efficiency eta will be dash. Option A unity, option B 0, option C infinite, option D zero point 0.5 to zero point 0.6. This is similar to the last question. Here also the gaseous phase in the tubular gaseous phase flow in the passes in the tubular pattern inside the reactor under the pneumatic conveying condition. So therefore the contact efficiency is again unity. So in the last question it was about plug flow pattern. So if the gas passes in a plug flow up the reactor, the constant efficiency will be unity. And in this question again, okay, unity. And in this particular question again, it is about gaseous phase passes in a tubular flow pattern in the reactor under a pneumatic conveying condition. So the contact efficiency will again be unity. And here the main thing is particles are evenly distributed in the gas phase. So just a minute, I will be back. So again here we have it as unity. So that is for question 8. Question 18. So question 20. So we have the question 20. So here question 20 is the last question for problems from week 12. So it is a problem. So but it is a very simple problem, I would say. And we'll see the question and then you can answer. Consider the, oh, where is my cursor? Yeah. Consider the first order reaction A giving B, which was carried out at 25 degrees Celsius and 1 atmosphere. If the molar flow rate is 50 moles per second of pure A, calculate the volumetric flow rate of feed gas. So here what are all the things given? First order reaction A to B, and it was carried out at 25 degrees Celsius and the pressure is 1 atmosphere. So the molar flow rate of the feed is 50 moles per second of pure A, and we are asked to find the volumetric flow rate of feed gas. So feed is given as pure A and A is giving B at the conditions 25 degrees Celsius and 1 atmosphere. So the molar flow rate of A is 50 moles per second. So the reactant feed is molar rate is 50 moles per second. So we just need to convert it into volumetric flow rate of feed gas. And options are option A 5 meter cube per second and option B 7.51 meter cube per second, option C 6 meter cube per second, option D 1.22 meter cube per second. So I'll repeat whatever the things that are given and I'll give you guys a 1 minute time so you can just solve because it is a very simple problem. So first one, it is we are asked to find the volumetric flow rate of feed gas in meter cube per second. So looking at the options, we can see that the answer that is expected out of us is in meter cube per second, and it is A giving B, and the reaction condition is 25 degrees Celsius and pressure 1 atmosphere, and molar flow rate is 50 moles per second of pure A. So I'll give you guys 1 minute so you can just get the answer and we'll see how to solve it later. We'll see how to solve it once you guys get an answer. So answer is actually option D, 1.22 meter cube per second. I hope most of you would have got the answer right. So we'll see the solution procedure first. First, let us write the given. Given things are 50 moles per second of pure A. So it is molar flow rate of pure A is given. So the feed is actually pure A. So like if we calculate for A, it is sufficient. We will get the volumetric flow rate of A. So we are just asked to convert this molar flow rate to volumetric flow rate. So N is 50 moles per second. And temperature is 25 degrees Celsius. In Kelvin, it is 298 Kelvin, 273 plus 25 degrees Celsius. And pressure is 1 atmosphere or 101.325 kilopascal or 101.325 into 10 power 3 pascal or 1.01325 into 10 power 5 pascal. So whichever it is, all these things are the given. And now what are we to find? We have to find the volumetric flow rate of feed gas, that is Q. So here feed is nothing but pure A. So pure A is given in molar flow rate, that is moles per second. So we need to identify the volumetric flow rate. So Q we need to find, and formula, we all know the formula for ideal gas. Ideal gas equation is PV is equal to nRT. So in this equation, N is number of moles, R is gas constant, T is temperature, and P is pressure, V is volume. So now here instead of volume and moles, we are just using the volumetric flow rate and the molar flow rate. So PQ is equal to N dot RT, or in other words, Q is equal to N dot RT by P. This is what we have written over here. PV is equal to nRT is the ideal gas formula. And instead of rearranging this equation, we will obtain V is equal to nRT by P. V is equal to nRT by P, and if instead of using volume and moles, we are using volumetric flow rate and molar flow rate, we will be getting the equation as Q is equal to N dot RT by P. So here we have all the required things, that is we know Q, we know N dot, we don't know Q, but we know everything in the RHS side. That is N dot we know, R we know, T we know, and P also we know. So R is nothing but gas constant, so its value is 8.314. R is gas constant and its unit is 8.314. Joules per mole Kelvin is the unit. R is 8.314 joules per mole Kelvin. So Q is equal to N dot is 50 into 8.314 into T is 298 divided by 101.325 into 10 power 3. So substituting everything, we are getting the value as 1.222 meter cube per second. So we'll just check the value of R, unit of R. Where is my cursor? Here, yeah. I am saying its unit is joules per mole Kelvin. And we have Q is meter cube per second. In the RHS side, we have moles per second, and into R, Newton meter is joules, so I am writing in that form, Newton meter per mole Kelvin, into R into T, so it is Kelvin divided by P. P is pressure, force per unit area, Newton per meter square, Newton per meter square. So we have moles and moles get cancelled. K gets cancelled. Second will remain. It will remain. Newton gets cancelled. And meter by 1 by meter square. So it becomes meter cube per second. So yeah, LHS and RHS unit matches. I was just confused and not confused. I just wanted to confirm the unit of R. That's it. So if you have any doubts in these things, you are also like you can also confirm the units. So you will be very confident of the terms you are using in the equations as well as the procedure you are doing. In like it won't help all the time, but it would be like help you confirm if you have any doubts at some point. So answer is 1.22 meter cube per second. So we'll go back. So answer is option D. So I'll give you guys a quick recap of things. So we are asked to find the volumetric flow rate of feed gas, and for that we are given molar flow rate, temperature and pressure. And we are using the ideal gas formula. Pb is equal to nRT, V is equal to nRT by P, or Q is equal to n dot RT by P. So here Q is the volumetric flow rate of gas and n dot is the molar flow rate of gas into RT by P. So R is 8.314 joules per mole Kelvin, and we are substituting that. Okay. So substituting everything, we are getting the value as 1.22 meter cube per second. So I'll just put R value over here. R is equal to 8.314 joule per mole Kelvin. So just to like use, just for your use if you are using these slides at later point. So that is it. So we have covered the problems till week 12. So now we have actually 12 more problems from week, 15 more problems from week 11. So for that actually, we'll start after taking 5 minutes break. So the time now is 4:03. We will start by 4:08. I'll be back in 5 minutes. You also take a 5 minutes break and we'll see. So we'll start with week 11 problems now. The first problem is about what is the unit of dispersion coefficient? Meter per second square, meter per second, option C meter square per second square, option D it is meter square per second. So the answer is actually meter square per second. Option D is the right answer. Dispersion coefficient is frequently modeled as the product of fluid velocity and some characteristic length scale. So dispersion coefficient, if it is equal to product of velocity and some length scale, what is units would be meter per second into meter, it would be meter square per second. We have only 15 problems from week 11 and these are very simple problems. Apart from few problems, few numerical problems, most are just asking formula or unit or something like that. Apart from that, it is a very simple things. So I just hope you have completed the assignment 11, week 11 assignment. So it was very easy actually compared to the rest. The problems here were very straightforward. Excuse me, just I was. So yeah, question 2 it is about what is the correct expression for Schmidt number where mu, rho and d represents viscosity, density and diffusivity respectively. So we have Prandtl number, Schmidt number, Reynolds number, Sherwood number, Nusselt's number and so many dimensionless number. They especially come into picture when we are dealing with the mass transfer and the heat transfer phenomena. So, Schmidt number mostly associates in the mass transfer and similar thing would be the Prandtl number. So here Schmidt number, so we are asked to find the correct expression. So option A it is Schmidt is equal to rho g into d by mu and B it is mu by rho g d and option C it is Schmidt is equal to d by mu rho g. Option D it is Schmidt is equal to mu rho g by d. Answer is actually kg per meter cube into meter square per second. Answer is option B is the right answer. Schmidt is equal to mu by rho g d. So one way to approach this is you should actually remember all the dimensionless number and their formula and their significance. So it would be helpful to wherever you go in the chemical engineering field. But apart from that, if you have any doubts, you can actually use some simple dimensionless approach. So here it is mostly option A and B would be same and B and C and D is same, just the numerator and denominator exchange. So in the C it is given that where is my here? Okay, C it is given d by mu rho g. So d is meter square per second and mu is kg per meter second and here it is kg per meter cube. This is not leading to dimensionless number here, so we can cancel option C and option D as the wrong ones. Only we need to identify between option A and option B because both of them would give the same kg per meter second divided by kg per meter cube into meter square per second. Both of them would be kg per meter second and will get cancelled. So since A is reverse of B, we need to identify between one of them. But it would be easier for you guys to eliminate certain options from this. So that is the approach. So option B is the right answer. Schmidt number is the ratio of kinematic viscosity to the molecular diffusion coefficient. So kinematic viscosity is nu. Nu is mu by rho. So it is nu by d. So Schmidt number is nothing but the ratio of kinematic viscosity to the molecular diffusion coefficient. So it is nu by d, and therefore it is mu by rho d. So I hope it is clear. So option B is the right answer. Now we will go on to question 3. Excuse me. So question 3, it is about which of the following is a wrong statement regarding the mass transfer coefficient under a single sphere condition. So which of the following is a wrong statement regarding the mass transfer coefficient under a single sphere condition? Option A, it is proportional to the diffusion coefficient of the gas. Option B, it is inversely proportional to the diameter. And option C, it is inversely proportional to the mole fraction of the inert component. Option D, none of the above. It is actually option B, E, D, none of the above. Okay, answer is option D. Mass transfer coefficient under a single sphere condition is none of these statements are wrong. That is, the mass transfer coefficient under a single sphere condition is proportional to the diffusion coefficient of the gas. It is inversely proportional to the diameter, particle diameter, and also it is inversely proportional to the mole fraction of the inert component. So none of the above is the right answer. So option, we will go on to question 4. Sherwood number is equal to, Sherwood number is equal to K into dpy by d. So K is inversely proportional to dp, diameter of the particle, inversely proportional to the mole fraction of the inert component, and it is directly proportional to the diffusion coefficient of the gas. Here K is the mass transfer coefficient, and therefore K is equal to Sherwood number into D, that is diffusion coefficient, divided by dp into y. So K is directly proportional to the diffusion coefficient of the gas, K is inversely proportional to the particle diameter, and K is inversely proportional to the mole fraction of the inert component. So all of the statements are true. So answer is none of the above is the right answer. Moving on to question 4, we have total exterior surfaces Sx of particles of all individual particles in the bed as per Kuhn-Levenspiel is given by dash. Option A, Sx particles, that is total exterior surface of the particles, surface area, exterior surface area of the particles is equal to V into SEG into 6 into 1 minus 5s, segment, V segment into 6 into 1 minus 5s divided by epsilon bed into d sphere. Option B, exterior surface of the particles is equal to V seg into 6 into 5s into d sphere divided by 1 minus epsilon bed. Option C, total exterior surface is equal to V seg into 6 into 1 minus epsilon bed divided by 5s into d sphere. And option D, none of the above. So my guess is C. Option C is the right answer. So total exterior surface area of the particle is equal to V segment, that is volume of the segment, into 6 into 1 minus epsilon bed divided by 5s into d sphere. So here it is volume of the particles is given by V seg into 1 minus epsilon bed. And why? Because epsilon bed is the void fraction in the bed. 1 minus epsilon s, epsilon bed gives the particle fraction in the bed. Particle fraction into volume of the segment gives the volume of the particles in the bed divided by the diameter of the particle, and the particle sphericity gives the total exterior surface area of the particles. So answer is option C is the right answer. So V segment into 1 minus epsilon bed gives the volume of the particles in that segment. So now moving on, we have question 5. Question 5 is about what is the sphericity of the spherical particle. Phi is equal to 0.5, phi is equal to 1, phi is equal to 0, phi is equal to none of the above. So this is a very simple question. We have been seeing this question for a very long time. I mean, not really the question, but we know the concept of sphericity. Sphericity is a factor which is used to determine how far the particle's shape is from the original spherical particles. So if phi is less than 1, we call the particles as non-sphere, and as these particles move away from the spherical particles, I mean as the value deviates from the phi is equal to 1, the more the non-sphericity of the particle is. So therefore, for the spherical particles, phi is 1. So the comparative factor or whatever it is, the sphericity for the spherical particles is 1. Phi is equal to 1 for spherical particles. Option B is the right answer. Question 6, it is about what will be the sphericity of the particle that is not sphere. Option A, phi is equal to 1. Option B, phi greater than 1. Option C, phi less than 1. Option D, none of the above. Again, this question we have seen only now. As phi value decreases, the more the non-spherical particles are. So phi is less than 1 gives the sphericity of the particles that is not sphere. So phi is equal to 1, that is sphere says sphericity of the particles. Phi less than 1, it is the particles sphericity for particles which are not sphere. So option C is the right answer. Moving on, we have question 7. In question 7, what is the unit of mass transfer coefficient? So answers options are meter per second square and meter square per second, and it is meter per second, none of the above. So the answer actually is meter per second. So I'll give you a small hint actually. Sherwood number, how do we define it? Equal to K into dP into mass fraction divided by D. In this, Sherwood number is dimensionless and we need to find the unit of K, mass transfer coefficient. dP, diameter of the particle, and Y doesn't have unit, and D is meter square per second. So this meter and this square gets cancelled, and therefore K is the unit of meter per second. If you don't know certain units but you remember certain other units, you just try to correlate any formula and get the value, get the unit for that. The answer is option B is the right, C is the right answer, meter per second. So now we will move on to question 8. Calculate the Sherwood number for naphthalene particles of diameter 2.5 mm. Use Rand's 1952 expression. Data U is equal to 0.5 meter per second. Rho G is 1.18 kg per meter cube. Nu is 1.8 into 10 power 5, 10 power minus 5 kg per meter second. Schmidt number is 4.8. So in this question we are asked to find the Sherwood number, and the particle diameter is given as 2.5 mm, and we are asked to use the Rand's expression, 1952 expression, and we are given the velocity of gas and gas density and gas viscosity gas density is 1.18 kg per meter cube and mu is 1.8 into 10 power minus 5 kg per meter second. So air is the fluid and Schmidt number is given as 4.8. Sherwood number, we all know it is K into dP into Y by D. So all the factors are not given explicitly, so we are asked to use the Rand's expression. So options are Sherwood number is 5.55, Sherwood number is 11.16, Sherwood number is 2.98, option D Sherwood number is 10.10. Again it is a simple approach, so I'll give you guys a minute time and try to solve that. We will solve that after 1 minute. So option answer is actually option B is the right answer, that is 11.16. So we will see how to solve that. Question 8 solution. So we are given U is 0.5 meter per second and rho g is 1.18 kg per meter cube and mu is 1.8 into 10 power minus 5 kg per meter square kg per meter second and Schmidt number is 4.8 and diameter of the particle is 2.5 mm. So we are asked to find the Sherwood number. So formula we are going to use is Rand's 1952 expression. Sherwood number is equal to 2 plus 0.6 into Reynolds to the power of 1 by 2, Schmidt to the power of 1 by 3. So here Sherwood number is a function of Reynolds number and Schmidt number. Similarly, if you are dealing with heat transfer coefficients, it would be Nusselt's number as a function of Reynolds number and Prandtl number. So those things you keep in mind when you are solving that. Coefficients might be differing, but mostly the approach would be the same and the functional groups would be the same. For mass transfer, it is Sherwood number as a function of Reynolds number and Schmidt number, and for heat transfer, it is for heat transfer, it is Nusselt's number as a function of Reynolds number and Prandtl number. So moving on, we have the calculations. First, we need to know the unknown terms. Schmidt number is directly given, but Reynolds number is not directly given. So Reynolds number is the form rho v dp by mu, rho v d by mu. So here rho is 1.18, u is 0.5 meter per second, dp is 2.5 into 10 power minus 3 and mu is 1.8 into 10 power minus 5. So Reynolds number we are calculating it as 81.94 and then we are substituting the Reynolds number in the above equation. Sherwood number is equal to 2 plus 0.6 into Reynolds number, that is 81.94 to the power of 1 by 2 and 4.8 to the power of 1 by 3. So we are getting the value as 2.92 plus 9.16. So answer is 11.16. So it is a very simple problem. So what are we doing here? We are just given the fluid flow velocity and we are given the density of gas, viscosity of gas and Schmidt number and particle diameter. So we are asked to find the Sherwood number. So Sherwood number is a function of Reynolds number and Schmidt number. So we know the Schmidt number because it is given directly in the question, but we do not know the value of Reynolds number. So Reynolds number is a formula we know, rho v dp by mu. So rho v dp by mu, all values are given in the question itself. So we are just substituting and getting the value of Reynolds number as this 81.94, and substituting back in the formula gives us the value of Sherwood number as 11.16. So answer is option B is the answer, that is 11.16 is the right answer. So I hope it is clear. So calculate the Sherwood number for naphthalene particles of diameter 2.5 mm. Use Rand's expression, and given data is U, that is fluid velocity, rho g density of fluid, mu viscosity of fluid, Schmidt number. So Sherwood number is equal to K into dP into Y by D. So we do not know certain factors in that expression, that is we do not know the value of mass transfer coefficient, and diffusion coefficient values are also not given. And also in the question itself it is mentioned use Rand's 1952 expression. So we are going to use that. So given we have written and we are asked to find the Sherwood number. Sherwood number is equal to 2 plus 0.6 into Reynolds number to the power of 1 by 5 and Schmidt number to the power of 1 by 3. And we are just substituting everything because we do not know the value of Reynolds number. Therefore, we have found the Reynolds number and we are calculating the Sherwood number. So, Sherwood number is equal to 11.16 is the right answer. Now, we are going to see the question 9. In question 9, determine the Schmidt number for naphthalene particles of diameter 1.2 mm with diffusion coefficient 0.086 centimeter square per second, and the data is viscosity of gas is 1.8 into 10 power minus 5 kg per meter second, and density of gas is 1.18 kg per meter cube. So we are asked to find the Schmidt number. Similarly, I will give you guys a minute time and you find the answer. Before that, I will give you the option. Option A 1.77, option B 2.55, option C 3.98, option D 5.87. So in the question, it is asked to find the Schmidt number, and diameter of the particles is given as 1.2 mm, and diffusion coefficient is given as 0.086 centimeter square per second. Viscosity of gas and density of gas is given. So you need to find the Schmidt number. So I'll give you a minute time. Just solve it in a pen and paper. Even if it is wrong, you will get the approach right. But the answer is very straightforward. It is just a substitution problem if you know the formula for Schmidt number. So answer is actually 1.77. So it is just a direct substitution problem to be. So we'll see the solution. First, in the given it is diameter of the particle is given as 1.22 mm and diffusion coefficient is given as 0.086 centimeters square per second, and viscosity of the gas is given as 1.8 into 10 power minus 5 kg per meter second, and density of gas is 1.18 into kg per 1.18 kg per meter cube. And we are asked to find the Schmidt number, and Schmidt number is formula is mu by rho g d. So this formula actually we have seen in a previous problem. So there also I have mentioned Schmidt number is again a dimensionless number. So if you are unsure of the formula like slightly, you can use a dimensionless approach to check whether it is right. But I would give you a tip: always remember all the dimensionless formula. It would be always helpful. So if you are a UG student or even PG student, like it would be very helpful to remember all the dimensionless formula. Like if most of the places you would be using any one of the formula. So yeah, so now we are going to substitute. Schmidt number is equal to mu divided by rho g d, and just substitution, mu is 1.8 into 10 power minus 5 divided by rho g is 1.18 into 10 power 1.18 into d is 0.08 centimeter square. So in order to make the all the units same, it is 0.086 into 10 power minus 4. So we are just converting here into 1 equal to 1.77. Hope it is clear. The question we are given the particle diameter, diffusion coefficient, and viscosity of gas and density of gas. So we are asked to find the Schmidt number. So in order to find the Schmidt number, we need to know the formula. Formula is Schmidt number is equal to mu divided by rho g into d. So mu we know viscosity of gas, rho g we know 1.18 kg per meter cube, and diffusion coefficient we know 0.086 into 10 power minus 4 meter square per second. We are just converting the unit, and it is calculations. Schmidt is equal to 1.8 into 10 power minus 5, that is viscosity, divided by rho g is 1.18 into 0.086 into 10 power minus 4. So we are getting the answer as 1.77. So looking back at the question, we know the answer is option A is the right answer. 1.77 is the right answer. I hope it is clear for everyone. So now we will go to question 10. Gas is passing at a gas velocity of 0.04 meter per second through a fixed bed of particle size 2000 micrometer. Calculate the Reynolds number of the particle. Data: density of gas, rho gas is 1.225 kg per meter cube. Viscosity of gas, mu gas is equal to 1.81 into 10 power minus 5 kg per meter second. So here again, it is the simplest problem, I would say. I hope most of you had done it while submitting the assignment. So coming back, here we are passing the gas through a velocity of 0.04 meter per second, and we are passing it through a fixed bed of particle size 2000 micrometer. And the Reynolds number of the particle is, we are asked to find the Reynolds number of the particle. So we are given the gas velocity and particle size and density of gas and viscosity of the gas. So answer is, we'll see. Before that, if we look at the option, Reynolds number of particles is 10.41, option B 5.41, option C Reynolds number of particles is 11.41, option D Reynolds number of particles is 7.41. I'll give you guys a minute time. Mostly it won't be that, you won't require that much time, but still try to get the answer. We'll see. It is the simplest problem, I would say. So answer is actually option B is the answer, that is Reynolds number of the particle is equal to 5.41. So we will see the solution. So first one, it is velocity of the gas is given 0.04 meter per second and diameter of the particle is given 2000 micrometer and density of gas is 1.225 kg per meter cube and viscosity of gas is 1.81 into 10 power minus 5 kg per meter second. And we are asked to find the particle Reynolds number, and Reynolds number of the particle is equal to rho v dp by mu. So rho is 1.225 kg per meter cube, u is 0.04 meter per second, dp is 2000 micrometer, 2000 into 10 power minus 6 meter, mu is 1.81 into 10 power minus 5 kg per meter second. So calculation 1.225 into 0.04 into 2000 into 10 power minus 6 divided by 1.81 into 10 power minus 5. So answer is 5.41. So answer to the above problem is 5.41. That is option B is the right answer. So we all know the formula for Reynolds number. So it is a very straightforward approach. Reynolds number is equal to rho into V into dP by mu. So rho is density of gas, V is velocity of the gas, dP is diameter of the particle and mu is the viscosity of the gas. So answer is formula is this and calculation is such that. So now this is approach and now we are asked to find go question 11. A rectangular fluidized bed of length 0.6 meter and width 0.25 meter and depth 0.04 meter is filled with the spherical particles of 0.5 mm. Width of the bed is 0.45. Determine the total exterior surfaces of all the particles in the fluidized bed reactor. Use the Cooney and Levenspiel expression. Option A, exterior surface of the particle is 39.6 meter square. Option B, exterior surface area of the particle is 19.6 meter square. Option C, exterior surface is equal to 29.6 meter square. Option D, 79.6 meter square. So we are asked to find the total exterior surfaces of all the particles, and inside the fluidized bed of length 0.6 meter, width 0.25 meter and depth 0.04 meter, and it is filled with spherical particles of 0.5 mm. Width of the bed is 0.45. So actually this formula we have seen in the previous slides, so it is very easier for you guys to to get the answer if you remember the formula which we have used in the previous slides. So again, go and recollect the formula and get me the solution. So we will discuss the answer in the in after 1 minute. So answer is actually option A is the answer, that is exterior surfaces of the particles is 39.6 meter square. So actually question 11 solution. We are given the bed dimension, length is 0.6 meter, width is 0.25 meter and depth is 0.04 meter and diameter of the particles is 0.5 mm, epsilon bed is 0.45. So we are asked to find the exterior surface of the particles, and for that we know the formula as V segment is equal to 6, V segment into 6 into 1 minus epsilon bed divided by 5s into d, diameter of the particle. So V segment is equal to volume of the segment 0.6 into 0.25 into 0.05, length into width into depth. So it is 0.006 meter cube, and since it is mentioned particle as sphere, phi s is equal to 1, and therefore surface area of the particle is equal to 0.006 into 6 into 1 minus 0.45 divided by 1 into 0.5 into 10 power minus 3. So answer is 39.6 meter square. A rectangular fluidized bed of length 0.6 meter, width 0.25 meter, depth 0.04 meter is filled with spherical particles of 0.5 mm size, and voidage of bed is 0.45, and we are asked to find the total exterior surfaces of all particles. So we are getting the answer as 39.6 meter square through the calculation. And how did we get that? We have just given the written and we are asked to find the exterior surface of the particles, and formula is volume of that segment into 6 into 1 minus epsilon bed divided by 5s into dp. So volume of segment we need to multiply length into width into depth, and we are getting it as 0.006 meter cube, and epsilon bed is directly given as 0.45. Phi s is the sphericity of particle, which is 1 for spherical particles. D sphere is diameter of the particle, which is given as 0.5 mm. So it is 0.5 into 10 power minus 3 meter. So substituting everything, we are getting the value as 39.6 meter square. So moving on to question 12, we have select the correct expression for the interchange coefficients. Option A, where KBE, KBC, KCE denote the interchange coefficient between the bubble and emulsion, bubble and cloud and emulsion respectively. Option A, KBE is equal to KBC plus KCE divided by KBC, KCE. Option B, KBE is equal to KBC plus KCE divided by KBC minus KCE. Option C, KBE is equal to KBC minus KCE divided by KBC plus KCE. Option D, KBE is equal to KBC KCE into KCE divided by KBC plus KCE. So the right answer is actually option D is the right answer. KBE is equal to KBC into KCE divided by KBC plus KCE. You can rewrite it in another form also, that would be easier for you to remember. 1 by KBE is equal to 1 by KBC plus 1 by KCE. I'll show you. So we are saying D is the right answer. So here KB is equal to KBC into KCE divided by KBC plus KCE. So I am just taking in both the side. So it would be 1 by KBE equal to KBC plus KCE divided by KBC plus KCE, that is equal to 1 divided by into KCE plus 1 divided by KBC. It is easier to remember this than this. So KBE is equal to KBC into KCE divided by KBC plus KCE. So here we are asked to find the interchange coefficients given KBE, KBC, KCE. So KBE is between emulsion and the bubble, and KBC is bubble and cloud, and KCE is cloud and emulsion. So bubble and emulsion we are taking in the one side and the rest we are taking in the other side. So I hope it is clear. Now we will move on to question 13. Question 13, it is asking what is the unit of interchange coefficient between bubble and cloud? Meter square per second, 1 by second, option C meter per second square, option D none of the above. Answer actually is 1 by second. It is the unit of interchange coefficient between bubble and cloud. So the unit of interchange coefficient is 1 by second. And moving on to question 14, we have calculate KBC for the operating conditions. Minimum fluidization velocity is given as 0.02 meter per second and D is 2.5 into 10 power minus 5 meter square per second. D is the interchange mass. D is actually diffusion coefficient, and epsilon mf is 0.52, dB is 4 centimeter, G is 9.81 meter per second square. So we are asked to find the KBC and we are asked to use Davidson and Harrison expression. Option A, KBC is equal to 5.14 per second. Option B, KBC is equal to 15.24 per second. Option C, KBC is 10.55 per second. Option D, 12.14 per second. So again, I'll give you guys a minute time and get the correct expression and we will solve the answer. So answer actually is option A is the right answer, that is 5.14 per second. Solution wise, it is we are given minimum fluidization velocity is 0.02 meter per second. The diffusion coefficient is 2.5 into 10 power minus 5 meter square per second. Epsilon mf is 0.52. dB diameter of bubble is 4 centimeter or 0.04 meter. G is 9.81 meter per second square. And we are asked to find KBC, and formula for KBC is equal to 4.5 UMF by dB plus 5.85 into D to the power of 1 by 2 G to the power of 1 by 4 divided by dB to the power of 5 by 4. So this formula we need to remember, and this is the formula for finding the interchange coefficient between the bubble and the cloud, and formula is 4.5 UMF divided by dB plus 5.85 D to the power of 1 by 2 G to the power of 1 by 4 divided by dB to the power of 5 by 4. So important things to be noted over here are we need to remember the formula because there are too many parameters in the formula and too many coefficients to remember. So calculation, we are just substituting everything. UMF we know 0.02, dB we know 0.04 meter, 5.85, d 2.5 into 10 power minus 5, and g is 9.81, and dB is again 0.04. So we are just substituting and we are getting the value as 5.14 per second. So answer we are getting 5.14 per second. I hope it is clear. Option A is the right answer, 5.14 per second. So we are just given, we have written the given, and we are asked to find KBC, that is the interchange coefficient between the bubble and cloud. And formula is KBC is equal to 4.5 into UMF divided by dB plus 5.85 into d into 1 to the power of 1 by 2 g to the power of 1 by 4 divided by to the power of 5 by 4. So I hope it is clear. Only thing we need to remember is we need to remember the formula for this particular problem. If we remember the formula, it is rest is a direct substitution, so it is not an issue. So moving on to question 15, that is the last question for today's session. Question 15 states that the value of interchange coefficient between bubble and cloud and emulsion is 4.55 per second and 2.51 per second. Determine the interchange coefficient between bubble and emulsion. So the formula we have seen in a problem, two problems before. So now we are just going to substitute the values in that particular formula and get the answer. So likewise, options are 3.21 per second. Option B, KBE is equal to 5.52 per second. Option C, KBE is equal to 1.62 per second. Option D, KBE is equal to 4.32 per second. And I'll give you a 1 minute time, and you people let me know the answer, because the formula we have seen two problems before only, so it should be easier to calculate the answer. And I have given you a direct, more easy way to remember the formula also. So we'll see the solution. Answer is option C, KBE is equal to 1.62 per second. And steps are KBC is given as 4.55 per second and KCE is 2.51 per second. So we are asked to find KBE, and KBE formula we know from two problems before as this KBC into KCE divided by KBC plus KCE. So we are just substituting now. KBE is equal to KBC into KCE, that is 4.55 into 2.51 divided by 4.55 plus 2.51, which is giving us the answer as 1.6176 or 1.62 per second. 1.62 per second. So answer is option C is the right answer. The value of interchange coefficient between bubble and cloud and emulsion, that is KBC, is 4.55 per second and KCE is 2.51 per second. Determine the interchange coefficient between bubble and emulsion. So KBE is equal to KBC into KCE divided by KBC plus KCE, or in other words 1 by KBE is equal to 1 by KBC plus 1 by KCE. KBC is 4.55 per second and KCE is 2.51 per second, and we are substituting everything back in the formula and we are getting the value as option C. KBE is equal to 1.62 per second. So option C is the right answer. So option C is the right answer. So that is how we solve this particular problem. And now actually the time is up, and if you have any doubts please let me know, otherwise we can close the session. And I wanted to inform you two things. First thing is we'll have this since this week 12 session, and we have almost covered problems till week 12 in these 12 weeks. So problem wise this is helpful for assignments. So this is the last week for today's this course, that is a fluidization engineering course, but we have one more session next week from 3 p.m. to 5 p.m. So in that session we'll have a summary and we'll have few problems from all weeks. So if you have any doubts from all the weeks, like from week 1 to week 12, if you have any doubts, I'll be happy to take the questions in that class and we can discuss more on any topics you want. My plan is to have an overview of whatever we have seen till now and have the discussion on the week 12 assignment problems. And if you have any further things to be discussed, we can happily discuss that. And if you have any questions also, we can discuss in next week's class. So we have one more class next week from 3 p.m. to 5 p.m. next Saturday, that is 19th I guess. So mostly the timing would be next Saturday 3 p.m. to 5 p.m. If there is any change in timing, you would be informed through email from the NPTEL. So that is one thing. And if you have any doubts in today's session, let me know. I'll be waiting for one more minute. And this week actually we have lost one legend, Sir Ratan Tata sir. So prayers for him because he has done so much and he was always a visionary. So prayers for him and his circle. And yeah, that is. And also happy Dasara to you guys. Today is Dasara, so that is there. So yeah, if there is any doubt, please let me know or we can close the session. We have seen 2 weeks, two parts of 2 weeks problems. So mostly week 12 problems to help you submit the week 12 assignment on time. And in addition to that, we have seen the problems from week 11 as well, for which you have submitted the assignments. So that is the thing. And if you have any doubts, we can discuss next week also, like, or you can put it through the NPTEL course forum. So that is the thing. So now I am closing the session actually. Thank you guys for joining. We'll see you again next week. I am closing the recording also. Thank you for attending today's session. We will meet again next week.